Hi, everyone. It's good to be here again. I'm very much loved the panel before. Spank chain is amazing. I'm here to talk to you about different chains, meta blockchains. So a year ago, we started OpenST. We looked at the space, saw the rise of Ethereum, and I was working on it for a couple of years already. And so we judged that the value will come really from bringing people online. So we set ourselves the message and the aim to bring 1 billion new users to Ethereum. And we're going to do that by tokenizing mainstream applications. But the requirements for that are that we need scalable programmable money. And it also needs to be easy for millions of users to use and to adopt today. And just earlier this week, we actually moved version 0.92 of the protocol to mainnet. But what I'll be talking today about is, for the first time, OpenST Mosaic. So we consider scaling to consist of 3 parts. We want to scale for users to adopt the technology. We want to scale for developers to build against it with token engineering as a focus. But it also needs to scale at the transactions per second that we can process on Ethereum. And so some of the alternatives, a lot of people will know Plasma, but it's application specific and you run into a data availability problem. Payment channels don't satisfy our solution because you can't develop smart contracts against them. And then a lot of really good work has gone into sharding plus Casper. Raul talked earlier today about Ethereum version 2.0. That is amazing work. But it's future work. It also has high stakes, moving Ethereum from version 1 to version 2. And so what we want to contribute today is Mosaic. It's a concept of token sharding, which is layer 2 scaling on the existing Ethereum. And so also what I personally hope is that the work we're doing can very strongly contribute and feed back onto and in both ways, learning and testing ground for Ethereum version 2.0. So in the next few minutes, I will try to explain to you what Mosaic and a meta blockchain is. And so I'll give you the concepts now, and then I'll try to make them clear going forward. So Mosaic is a consensus protocol in order to run a meta blockchain on top of Ethereum. Each meta blockchain runs in parallel. The state space executes in parallel, and it injects that into Ethereum. And all of these meta blockchains are secured by Ethereum proof of work with an open staked validator set on top of Ethereum proof of work. And it's important that all transactions are asynchronously finalized and also committed back onto Ethereum. And then lastly, and this is actually a very interesting point to refer to the earlier talk, Mosaic has a message passing protocol between Ethereum and the meta blockchains so that we can actually talk between the probabilistic finalization of Ethereum proof of work and the economic finality that runs the meta blockchains. And so the problem we're trying to solve is bringing millions and eventually billions of new users onto Ethereum. And the obvious answer is blockchains do not scale. But DApps have the same problem. If we want millions of users to run on DApps, we need to make sure that Ethereum scales. And so actually the answer is quite clear. The number of transactions finalized does scale linearly with the number of nodes if we can shard the total space across the number of nodes, and also if you can offset the overhead incurred by more nodes relative to the gain you're making, right? And so the solution that we propose is to focus on asynchronicity, to make sure that there are no time constraints between the meta blockchain and Ethereum proof of work, and that's where I'll put the focus for this talk. And so we derive the security of Ethereum proof of work asynchronously to finalize and secure transactions on auxiliary chains. And to give you a short sense of why this makes sense, assume that Ethereum runs at 10 transactions per second, and you would have 100 of these auxiliary systems, each running 100 transactions per second, then you have 10,000 transactions. And in a very simple model, if there are 100 validators for 100 auxiliary systems, now you have 10,000 validators that need to commit to Ethereum. So that's 10,000 transactions that would take you 10 seconds and fully occupy, 1,000 seconds and fully occupy Ethereum. But you have also processed 10 million transactions and been 99.9% efficient. But we can do a lot better, because, as I said, your benefit will scale linearly with the number of nodes, but also your costs will scale, unless you can actually not require that you need to commit back to Ethereum. And so, as an example, if you would only commit back once a day, you have 800 million transactions finalized, and you're only using 1.2% of Ethereum, and so on. The less frequent you have to go back to Ethereum, the better for the system. So let's do that. Let's move all transactions off of Ethereum onto auxiliary chains. But hold on, sidechains, they've been around for years. What's new here? Right, and so to make the point, the meta blockchain is fully defined with a consensus engine in the core contract on Ethereum. Each meta blockchain has an open staked validator set. It has Byzantine fault-tolerant consensus rules that allow you, and this is the interesting part, to allow you to move the block formation of your meta blockchain off of Ethereum onto an auxiliary system. And then very importantly, we have a gateway protocol that allows you to marry the probabilistic finalization of Ethereum proof of work with the economic finalization on the auxiliary system. And all value is always kept on Ethereum so that you can always recover. So that's what we call token sharding. It's an opt-in system where with ERC20 tokens, you can move some of your tokens into the auxiliary system and back out. And what the gateway protocol absorbs or consumes is the state root of the opposing system. And we do the same for OST. If you stake OST and move it into the auxiliary system, then we actually turn it into the base token of that auxiliary system, which you use to pay for the gas price for executing your transactions. And so what we get is a full native Ethereum interface. You can write your normal smart contracts. They are executed on-chain, but it is now scalable. And so that is what we have today on mainnet. But the important point is we oracleize this between the two chains. And what the work of Mosaic is that we're presenting here is how to decentralize and that state root transfer and secure the auxiliary chain with Ethereum proof of work. A very brief word, because it is important, on how the gateway protocol works. So if you want to move some tokens, it's a message passing system, so you declare it on one side, and you can only confirm it with a Merkle proof against the state root of your origin system onto the auxiliary system. And you would logically have to do that again to progress both messages on both sides, and then it is logically sound. So you can stake tokens on one side and mint them on the other side. It's very expensive and long process because you're waiting for the state roots to absorb your state transfer. And so we can speed that up a lot by introducing a hash lock on both sides. So once it is declared and confirmed on both sides, you can progress it directly by revealing the secret. And then importantly also, there is a bounty and a fee into this process. So any message can always be completed by any other node because there is a reward structure for both sides to complete the message passing. So with that said, another quick introduction of Casper. So that shared research that was by Vitalik and Griffith. Sorry, Butrin and Griffith, I guess. End of last year. And so the important point that was put forward there is that in Byzantine fault-tolerant consensus, we can actually reach consensus on what is a justified and a finalized checkpoint, as I'll explain in a second, on already proposed blocks. So we take away what we can normally think of as the finalization procedure from the layer 1 validators and move that to a layer 2 validator set. And so they do that by casting vote messages that identify a source and a target and their respective heights. And then you can, as you see in the drawing, you can, if for each supermajority link, where 2/3 majority of the validators actually has cast this source and target message, you can build a justified chain and also finalize the checkpoints. And importantly, for each finalized checkpoint, you know that you cannot revert the history unless they would publish contradictory votes. And for those contradictory votes, you can very easily slash their stake. And so we achieve a layer 2 blockchain properties of safety and liveliness, which we will use in a second. So what are meta blocks? Remember that a block is a mechanism of moving the state of one system from sigma to a new state sigma prime. For proof of work, you do that by finding the nonce that seals the block. For proof of stake, you can do that with a majority vote. And so we define a new type of block. Namely, a meta block is composed out of 3 parts. It has a kernel, a transition part, and a seal. And so a kernel, because it's important, has the height and the parent, as you would expect for a normal block. It also will specify the change to the validator set. And interestingly, I'll touch on this later, there's a voted upon gas price that is valid for that whole block. Then the other part is the transition part, and it specifies a dynasty number. And the dynasty number, for you know, on the justified chain, the ping chain, spank chain, ping chain, you saw earlier, each time a checkpoint is finalized, the dynasty number increases. So you can think of it as a height, but it increases by 1 every time you finalize a checkpoint. And it also keeps track of the transaction route, all the transaction, effectively verifying all the transaction, a Merkle root of the full transaction list, and the total amount of gas used. And then our seal, like a normal proof of stake Byzantine fault tolerant system, has a 2/3 majority of the weighted votes attached to it. But how do we construct it now? And by construction, we'll also show the properties that I started out with. And so we can do this recursively. Assume that the block H1 has been committed. Then the kernel is already known in the smart contract. The height, the parent, is obvious. We have a list of the new validators, and we have voted on the gas price. And in parallel, and this is important, it happens independently, the same validators can be voting on the auxiliary system as if it was just a system on itself, and produce a justified chain by having 2/3 majority links on the different checkpoints. We can also track how much gas is used, what the total transaction route is in the smart contract itself. But then here comes the fun part. Now, every finalized checkpoint on the auxiliary system has a 2/3 majority of the validators, so you can actually propose a new block on Origin, on Ethereum mainnet. And there can be competing proposals, but they're now no longer forks of each other. They're just proposals to commit back to Ethereum at different heights on the justified chain, on different dynasty numbers. And then again, because we're leveraging Ethereum mainnet, we get automatically the property that the first proposal that confirms a 2/3 majority of the vote is the new meta block that is sealed. And the only thing we have to do for that is extend the slashing conditions with a very simple, trivial third slashing condition, namely that you cannot commit contradictory transition objects. And the interesting part of Casper that we leverage here is that the slashing conditions are entirely defined on themselves. If I see 2 votes, it doesn't matter where I'm evaluating that. They're well defined by the vote objects themselves. And that means that we can enforce the slashing conditions on Ethereum mainnet and we can have the stake on Ethereum mainnet about the votes that have happened on the auxiliary system. But if we have sticks to punish the validators, we also need carrots. And so we want to have build on the existing systems that we know work. And so the gas market works. So users pay for the transactions they execute to what we call the proposers of the auxiliary chain, right? They're the normal validators of that chain. They don't need to know about much else. They produce the blocks. And they receive the normal gas price from the users. But we additionally require them to pre-deposit for pre-funding the meta blocks. Because now, for all the votes that the Mosaic validators cast, we can have them be rewarded on the auxiliary chain. And it gives us a very nice consequence that the validators have to vote both on the auxiliary chain and commit to Ethereum in order to get to their reward. So they have to be a full participant in the system. Additionally, but we're getting a bit in the weeds, we have a gas target that forces the validators to commit back to Ethereum. I want to go into details, but I can't, so ask me questions later. And also validators can join or log out, so it's a dynamic validator set as you would want. So why build this, right? The first reason is now this gateway protocol can consume the state root finalized by the validators. But the interesting part is that users and also contracts can now pass messages, ERC20 tokens specifically, without any bridge or validator set confirming their specific transfer onto and off of the auxiliary system. And importantly, it's now also possible to just atomically swap them. Once they exist on the auxiliary chain, you don't have to go through the expensive process. You can just atomically swap very fast between and move across these systems. And it gives us a way to scale DApps by an opt-in mechanism of moving into these auxiliary systems and across them. But what happens when it all goes wrong? And this is an interesting slide because this is why. So there's a lot of similarities between Ethereum 2.0 and Mosaic, and where we can learn from each other. If you want to shard all of Ethereum and the whole state space, you cannot say this slide. But because you're doing token sharding, and users can move in and out, and the original definition of your token is on Ethereum mainnet, you can actually cover for the case where the validators fail to reach consensus. Because now any last finalized checkpoint can always be brought by anyone to be a committed state on Ethereum. The validator set can be challenged that the meta blockchain has halted, and all the value was always on Ethereum itself. So whether you come back 1 week later or 1 year later or 10 years later of the value you had or the state you had on the auxiliary system, you can always now present the proof that you had those tokens and release them from the gateway contract and recover them. So there's no mass exit problem either. And so to summarize, we are currently with 120 developer teams on testnet, and more than 10 of our external partners have moved quite recently now onto mainnet for early testing. With 093, we completed the gateway protocol of cross-chain messaging. And right now, our focus is on the OpenST JS part, so decentralized key management and the token rules engine. So I was on the token panel before. And also, we will start talking a lot more about Mosaic. And so by the end of the month, we will publish the paper. Right now, we're soliciting feedback from the community. So please, if you have comments, give them or questions. And so we'll keep building out the whole stack. And then early next year, we want to go to alpha with Mosaic, and shortly after to beta to warm up the validator pool. bringing more companies and more users online. And then also very interesting, want to have smart contract calls between auxiliary chains, which we currently don't support. And then we will put in a time lock by 2020 that then the validator pool is fully in control of the tokens. Well, sorry, the meta blockchains. And so thank you very much. It's a great opportunity to present this here for the first time. And we'll be welcoming your comments.